This is the Filament Extruder for 3D printer. This is Alex Bonasseur, Ian Felder, Joe McMahon, and Blake Bravo. Take it away, guys.
Thanks, Professor. Welcome, guys. We're excited to present to you today about our senior project, which, as Professor Zink said, is a filament extruder for 3D printing. So our senior project deals with 3D printing, specifically fused deposition modeling. So it's called FDM. This process uses a filament, which you can see going into that nozzle there on the screen. That nozzle is heated, and that filament is then deposited in a controlled motion in 3 dimensions to make your solid. So the plastic filaments that are usually used are ABS, which is what our machine will be using, and PLA is just 2 different types of plastic. The filament is a kind of a long string of plastic at a constant diameter. Industry standards right now are at 1.75 millimeters diameter and 3. And so there's a big cost discrepancy between filament spools, which you can see on the screen here, sold by MakerBot Industries, which is kind of the industry leader right now in hobbyist level 3D printers. They sell their spools for about $50 a kilogram. However, you can find raw ABS pellets from many distributors online for around $5 a kilogram, which Blake is going to hand out right now. So you can see that there's this cost discrepancy between these 2 different materials. And so we saw this as a problem in the market, and there's a need in the market to cut out this middleman. So we wanted to make a machine that would take pellets and extrude them, and this is what we've come up with. And this allows us to cut out the middleman, reduce the cost of filament, which reduces the biggest operating cost of 3D printing. This allows for more print jobs, so more prototyping and more small-scale manufacturing, and allows more hobbyist-level people to gain access to this technology. So we came up with a couple project goals that we wanted our machine to accomplish. First of all, as I said before, we wanted to reduce the cost of filament production. We also wanted the machine to be compact and serviceable. So most of these machines currently are in industry are very large, so we wanted to have a small footprint machine. We also wanted it to be serviceable. That is, we wanted to maintenance it. So if something goes wrong, we'll be able to take it apart and either clean it or fix something. We also wanted to continuously extrude filament. This is very important because 3D printing, as you saw on the first slide, FDM uses long strings of filament to make parts, and it needs to be a continuous string. We also wanted to have our filament be a constant diameter. We chose 1.75 millimeters as more and more hobbyist level 3D printers are going towards this size. We need this tight tolerance to be able to print parts accurately, and this tight tolerance in our filament translates to well-toleranced printed parts. As you saw on the spool in the last slide, filament is sold in spools that attach themselves to the backs of 3D printers. So we also had a goal in mind to spool our filament once it was extruded.
So here's our functional decomposition of our machine, just basically what it does. So we're taking pellets, an empty spool ideally, electricity and controls, and out we're getting our filament, some waste heat, and some waste plastic as well. And so level 1 for our machine, we start the machine, we heat up the machine. It takes about 45 minutes to an hour at this point. Right here is our die temperature. We like that at about 190 to 200 degrees Celsius. So we heat it up, we extrude the plastic, we spool that filament, and we stop. So here's the CAD design of our machine you see right in front of us. We feed the plastic into the feed section right here, which is covered by this hopper right here. Pellets are within there. So the plastic is fed into here. The feed screw pushes the plastics down into the barrel. The barrel is where it's heated right in here. And the plastic is then compressed by the feed screw more and pressed out through the die. So we're going to show you our heating section. So here, same exact picture, nothing has changed from our actual machine. You see 2 thermocouples. The thermocouple on top here is our barrel thermocouple, which you see right up here. It's at 230 now. Our band heater right here, which heats the barrel, and our thermocouple on the die right here, which is the reading here as well. You can see the filament coming out of the bottom right there.
So Blake just told you about the heating section. I'm going to describe the drive section to you. Can you go back? There's a motor back here that you can't really see that drives a small sprocket, which chain drives a large sprocket, And we have all this gearing so that we can get a very low rotational speed and a very high torque because we're pushing a lot of plastic. And that drives the screw in the middle. The bearing housing has some stuff in it, which I'll describe later, that lets it rotate freely. Next slide. So the question of why did we choose a screw extruder might come up. In polymer extrusion industry, there's a lot of different ways to extrude plastic. One of the ways is with a ram extruder, which a lot of you might be familiar with. It's common in plastic injection molding. And we immediately cross this off the list because it's not a continuous system. We need continuous extrusion, like Alex explained earlier. So this you'd have to reset every time if you wanted to make a very long filament. So we cross that off the list. The next way to do it in industry is with a disc extruder, which uses a lot of shear pressure and friction and a little bit of heat to heat up the plastic and then force it through the nozzle. This is a really complex system. It requires a lot of power. Usually they're very large. We didn't really like this option. And finally is the screw extruder. This is one of the most common methods of continuously extruding plastic. It's based on the Archimedes screw principle, which is rotational moment. Rotational motion produces linear actuation of the material within the webbing. In this picture, you can see the plastic would go in at the left and fill up the screw, and then it gets preheated. Then there's a vent port so air can escape, and then there's more heat, and finally the die where a lot of the pressure is and squirts out there. Sometimes these machines can be meters by meters. Sometimes they're used to produce plastic parts very large. Sometimes it's used for sheet plastic, all types of things. So ultimately, this is what we decided to go with. And here is a plastic model of our feed screw. It was made by Bob Shostrom as a proof of concept for our steel screw, which is inside of here. It's very difficult to machine. As you can see, so it goes like this in the machine. At the top, it's much thinner than at the bottom, so that more pellets can be grabbed by the webbing as it spins. And then the taper is so that the plastic compresses and air bubbles are forced up as the plastic moves down and is heated. So I'm going to hand that out so you guys can play it. And here's a cross-sectional view of our bearing housing, which is right here. This is important to make sure that everything can spin without any friction. So at the bottom there's a tapered roller bearing. That tapered roller bearing can absorb the normal force that the plastic puts back on the screw from being pushed. So it absorbs that force. It also absorbs a radial force, so that it keeps our screw concentric within the barrel. Then there's another bronze sleeve bearing, which also helps keep the screw concentric within the barrel. And finally, there's a lock nut and thrust bearing at the top. The lock nut keeps it from falling into the system, and the thrust bearing keeps the lock nut from putting any friction on anything. So with just this system, we could spin the screw very easily. You just kind of go and it would spin. Next slide. And so at the bottom, that's the bearing housing I just described. There's the screw and the lock nut, the large sprocket, which goes to the small sprocket in the motor. And here's a quick assembly video. Everything going on the screw, everything attaching to the barrel, the die, and everything attaching to the frame. Okay.
So now that we've discussed the functionality of our machine, I'd like to discuss the product we were able to produce. We successfully produced ABS filament, and I have 3 samples here. One is our sample, it's labeled as our product, and then I have 2 other samples that's commercially available filament. I have some dimension filament, which is for a high-end, very nice printer that BU has. That the filament costs $250 a kilogram, very expensive. And then I have some MakerBot Industries filament that sells for $50 a kilogram. So I'm going to pass these filament samples out so you guys can get a feel for how close we got to the real thing. Some of the factors that change the properties of our filament is what I'm going to go over next. The rate at which we can produce our filament depends on the speed of our drive system that Joe just described. which includes the gearing of our motor, as well as the die geometry, the pitch at which the threads on, the screw geometry, the pitch on the screw affects how fast the plastic is pushed per rotation of the system. The diameter of our extruded filament depends on a lot of different things. That was one of the hardest things we had to control. The largest factors controlling the diameter of the extruded filament are, firstly, the orifice diameter of the die, so the hole at the bottom of the die. That diameter sets the initial control point for the extrusion diameter. The things that change that are the back pressure within the system, which causes a phenomenon called die swell, which is where the filament expands after it's extruded. The quality of our filament really depends on the quality of our raw material. When you buy raw plastic pellets, you don't necessarily know what climates they've gone to and if they've been moisture controlled. So one of the steps before you extrude filament is a drying process to make sure there's low moisture content, because ABS readily absorbs moisture from the atmosphere. When you remove, the purpose of removing moisture is to get the water or air particles out of the plastic, because when you heat it to our operating temperature of 230 degrees Celsius, steam readily occurs and causes air bubbles or moisture bubbles. And the filament quality is also determined by the smoothness of the die hole. And the cost of our filament depends on the cost of our raw material, the cost of electricity to heat our system, and the operating time to run our system. Here's a slide that shows our filament quality compared to the purchasable commercial filament. Up at the top in the blue and red dots are the MakerBot and Dimension filament. They have a very tight tolerance control around their target tolerance of diameter of 1.75 millimeters. On the other hand, our product, which doesn't nail our target diameter exactly as far as we've gotten with our project, and we have a lot more variation in our product. But this shows that although it's hard to tell with the naked eye that our product isn't perfect, we do have a lot of variation. This data was collected by taking one data point per inch of 24 inches of filament, and those samples that are being passed around now are the samples that were used to collect this data. So, like I said before, two of the things that affects our filament diameter as it extrudes are these phenomenons, die swell and necking. Die swell occurs when you have a compressed fluid in a system, like we have a compressed plastic in our barrel, and that increases the density of the material. But when it's extruded out of the nozzle and enters atmospheric pressure, the density reverts to its original and expands. So that causes the filament to expand larger than the hole, as shown in this picture pretty well. The other effect that we had with our system is necking, or gravitational lengthening. When the filament was extruded, the weight of the filament below the next part to be extruded would pull and lengthen the product, which caused a shrinking of the diameter. So we have these two effects changing the diameter of our filament. Die swell, which increases the diameter, and necking, which decreases the diameter. We attempted to alleviate some of the necking effect by using a fan to cool our filament just as it left the nozzle in an attempt to freeze the material before it had a chance to elongate. And what we found when we did that was that the fan, although it froze the filament and stopped the necking, it caused the die temperature, which you can see on the bottom display, to drop drastically. We were operating around 170 degrees Celsius, which will work, but what that did was cause the die pressure to increase. Because the die was colder, the filament had a harder time squeezing through, increased the pressure in the system, and when the pressure increases in a system, the die swell percentage increased. So our attempt at stopping necking caused our die swell to increase. So we ended up creating a product that had almost 3 millimeter diameter filament because of the increased pressure in our system. Here's a picture that shows the effect of necking. I hope you all can see that the diameter is larger outside of the circle, and the weight of the filament below pulls on the filament and causes that thinning effect. So here's some quantification of the previous chart that I showed. As you can see, the Dimension and MakerBot filament really does a great job of holding tight tolerances around the target diameter. This is important because of the way 3D printers use filament. They have two knurled bolts that push the filament between them to the next die that they're extruded from. Our filament, although not perfect, does hit about half or twice the variation we shot for as our project goal. Our variation is 0.1 millimeters plus or minus, and our average filament diameter on the sample that's being passed around is 1.62 millimeters. So as I previously discussed, we had those two effects, lengthening and necking. And because our die orifice was exactly 1.75 millimeters, you can see that the necking or gravitational lengthening effect dominated the production of our filament because our extruded filament nominal diameter is less than our target diameter. So our necking overcame the die swell. So next I'm going to go over some microscopic surface analysis that we did for our produced filament. I took all three of the samples that are being passed out now and used a high-strength 200x magnification camera microscope to take a look at what the surface of our product looked like. In this far left picture, you can see the Dimension product, which is the very expensive $250 a kilogram product. It has a very pristine, almost perfect surface finish with no striations or cavities from bubbles, and that's sort of to be expected if you're going to spend $250 a kilogram. In the middle, we have our product that also has a pretty clean surface finish, not too many striations due to the very smooth bore on our die. But we do have these bubbles, and that's like I said before, from the moisture content in our ABS, as well as possibly some trapped bubbles. The bubble problem in 3D printing is not necessarily due to the type of bubbles we show on this slide. The bubbles that cause really large problems in 3D printing are bubbles that are trapped within the filament, that the air is still in there, because when you try and extrude that through a 3D printer nozzle, it will pop, and that causes a gap in the printed surface. These kind of bubbles affect just the surface, and they're really just cavities, or like half bubbles. And they've already popped, or they were just a cavity from the bubble, and they don't necessarily cause large problems with printing. So we feel like the surface finish of our product is good enough to be used in a printer if we could get our diameter to our target. And then on the far right, we have the MakerBot Industries filament, which has a much worse surface finish, which I feel must be due to some imperfections in their die surface finish, which causes those striations from extrusion. But we don't seem to see any bubbles like we do on ours.
So I'm going to go over the cost of the machine that you see in front of you here. The parts that we purchased altogether to build this machine were around $800. We were really fortunate to obtain a bunch of free components and materials, which include most of the heating controls. So those are the two displays and the dynamite to power our band heater, and as well as the Teflon heat break, which is the white plate that you see there. Obviously, we had mostly custom machine components, and so you have to take into account both machining time and as well as assembly time. And so with help of the machinists who worked on this project, we estimated this cost to be around $4,000. So in total, we value this machine at around $6,000. Our customer, Professor Gerald Fine, will hopefully use this in the new Epic Center at BU to produce filament. So we thought it would be important to look at the payback period of this machine. So we think that after 2 years of development, with obviously more costs, we could feasibly obtain an extrusion rate of 2 centimeters per second. We're at about 0.65 centimeters per second right now. And we think that with this extrusion rate and with more development and obviously more cost going into that, we could feasibly sell this machine to have a payback period of around 11 spools. That translates to a 7-day payback period. Now that is 7 days, 8 hours of continuous operation at 2 centimeters per second. So if you were to run this machine for that long, the savings from between the spools, which are $50 a kilogram, and raw material, which we would purchase for $5, if you made 11 spools, you would pay back this machine, which we think is a worthwhile investment.
So here's a picture of us taking apart the machine to prove that it's serviceable. That what you see right here is the Teflon. Did we skip a slide, by the way? Yeah. Did we skip a slide? We did. No? Okay. On the bottom you see is the Teflon. These are removed, and right there is the drive screw. That was taken off semi-molten in order to get it off, just to prove concept that it can be serviced. The ABS was stripped off and put back together. And so what did we accomplish? Did we meet all our goals? Well, we did reduce the cost of the filament from $50 or $250 per kilogram to our $5 per kilogram. We did make a compact machine. We really wanted a small footprint. We saw machines out there were very large, and so we really wanted to make something that could fit on a desk, could be used at home or an engineering firm compactly. We wanted to continuously extrude filament because we needed to allow for continuous 3D printing. And we did do that. We do have an extrusion rate at about 0.6, 0.7 centimeters per second, but that can change due to the gear ratio of the motor. We did not extrude at 1.75 millimeters plus or minus 0.05 millimeters. We got close, 1.62 plus or minus 0.1 millimeters diameter, and we did not spool the filament into 1 kilogram spools.
So moving forward, although we accomplished some of our goals, we still left some stones unturned. There are a few hot button items that we feel could be improved upon in our device. One of those is obviously the filament diameter, and we think with the implementation of a better closed loop control system, we could guarantee the production of 1.75 millimeter filament. We'd also would have liked to create a color mixing system. You can colorize ABS pellets. These pellets that we have and have passed around are natural colored, and they don't have any additives or dyes. And you can colorize natural ABS using HDPE, or high-density polyethylene color pellets, which you just mix in with the ABS pellets, and they add color to the system. We also never accomplished our spooling system, which turned out to be a lot more complicated than we had anticipated. We thought it would be important to incorporate some better sensing. Although we have good thermocouples to measure the die temperature and barrel temperature, we felt that we could have done a better job by placing our thermocouples closer into the system, like if we drilled holes into the die so we could actually measure the temperature right at the die instead of the edge of the die. We also thought it would be important if we could measure the pressure inside the system to better control the die swell, because die swell is directly proportional to the pressure in the system. If we could get a real number on the exact pressure within the system, we'd have a better way to control that. Like I said, a closed loop control system would help tie this whole system together and produce the right size filament. And we could accomplish that by measuring the output diameter of the filament as it's being produced, and use that to actively control the heat into the system and the drive speed into the system to control the pressure. And that, of course, also a goal would be to create faster extrusion rate to justify our previously explained payback period. We also feel that even though we didn't finish everything we wanted to, we've set this project up as a great legacy project for future senior design teams, as we've set up, built a lot of the foundations of a fairly functioning prototype for filament extrusion that, with the things we've just discussed, could be implemented to make a really functional, great product. We'd like to thank all of the people who collaborated with us and helped us achieve this project so far. Our professors, Professor Zink, our discussion leader, Professor Fine, our customer, Professor Barboni helped us with some fluids calculations for our mass flow rates and things of the liquid molten ABS problems that we had. We'd also like to thank the machinists who really made this project possible. Without you guys, Bob Shostrom, Joe Estano, Ryan Lacey, and Dave Campbell, we would not have been able to build such a functional machine without the expertise and knowledge that you guys provided to the production of this machine. And we'd also like to thank Steve Lilburn from Boston Scientific for providing some of the heating controls, and Russell Wynn from OEM Supply, our Wattler distributor, that provided us with some heating controls and sold us some band heaters for the use in our project.
So we'd like to run the machine now. As you can see, we've already got some passive extrusion coming out just from it being heated. So the band heater now is operating at about 230, and we have a die temperature on the outside of our die at 196.
So we'll run this, and we'd like to field some questions if you guys have.
So you might experience some popping in the ABS because we haven't run it for a while. So we get some air bubbles, and those go away within about a foot or two of extrusion.
Anyone have a question? Mike?
First of all, you guys did a great job. How would you do it, like, necking, I guess, real quick? Adding the tool, would you use that gravity that caused that?
I think we've been debating a lot about this. I think that if we can implement a cooling system like the fan again, and then put a spool afterwards, the spooling will get rid of the necking, and we can change our die. Our die is designed to just pop off, so we can machine a new die to better fit the geometry that we want. So we think with a fan, a new die, then we could input.
You have a point. The adding the spooling system adds a new extra complexity because the spooling creates tension, which is another form of necking, just like gravity does. Joe? The size of our pellets dictated the gap that we allowed in between the barrel and the auger, because we wanted to make sure that the pellets would still push down and not just float back up. We anticipate that you could take already printed components, grind them up to around the same size, and recycle them using the same system.
Also, on that note, a common practice in polymer extrusion is to take your feed material, the pellets, and pour them on a table. And if the angle it makes with the table is less than 45 degrees, that's a good sign that you won't have any problems. So we did that, and our file looks like this. Our file looks like that, rather. So that's less than a 45 degree angle. I don't know if that was clear.
That's cool. That was one of the modifications that the machinists helped us make to make sure that one of the things we did was make the die hole longer so we could guarantee that we had straight extrusion, so we didn't have a cornering effect to that quick surface. But you're right, the elongation of the die channel may help us hold that filament diameter. The trick is getting the die temperature just right so you can freeze the shape without jamming the system and increasing the die swell.
So these types of machines have been popular recently. Everyone's trying to solve this problem. And most of the designs we found out there are horizontal designs. We made a design decision to do it vertically for a lot of reasons. One of our big debates as well. When it comes out horizontally, you get the drooping effect. So rather than elongation, you get drooping, kind of like a sad, kind of like a smiley face. So it was really a debate between drooping and necking, which one we wanted to deal with, and we chose necking.
Ideally, some sort of redirection wheel towards the spooling system would alleviate a lot of the gravitational lengthening and should be obviously part of the spooling system, which would alleviate that problem. Yes, sir.
So the air pump, the way to
Inside, yes. You can usually see them. That sample that's passed around probably has one or two, and they're easy to find. If you snap the filament, it will crack right at an air bubble, and you can see the air bubble. When we turn the machine off and restart it, like we just did when we had to turn it on downstairs and then haul it up here, we found that we have a lot of air bubbles in our produced filament, which goes away after a few meters of filament production. We're not exactly sure why those air bubbles are coming when we shut the system down and turn it back on, but we know they're there and we can see them, but after a while of filament production, they do stop.
what is the ultimate risk?
The risk would be the surface finish on that 3D printed part might have a gap in it. If the filament where the bubble is being used as a perimeter extrusion, it might pop, which would stop it from extruding, and the head would keep moving, and then it would extrude again, and there would be a gap. And if you were, say, trying to print a part that was waterproof, you might have a little bit of trouble maintaining the surface to be consistent. So,
Yes. Hand me that bearing. So initially we had the bearing, the brass knee bearing that's right up here in our bearing housing, and we replaced it with this bronze sleeve bearing. As you can see on the inner diameter, those are threads that were cut into that from the threads on the screw, and that's because that bronze expands twice as fast and twice as much as the bearing housing. And so in the future, that absolutely needs to be eliminated. And so what we have now is a smaller version of that. What we experienced was just seizing of the motor. The current would get too high, and you just hear the motor seizing. And that was the maintenance that we did. Pulled it apart and removed that bearing.
Put a new one in.
by replacing the bearing with a larger bearing, larger on the inside, smaller on the outside, when it expanded, it didn't seize up against the walls. We have a working machine that we can show you today. We ran it yesterday for an hour without any problem. Either way. Cool. It could obviously get very complicated. This is a constant speed motor. The torque reading on that power supply is a rating of the current reading is a torque. So the higher the current, the more torque. So if it's jamming, it'll have a higher torque. If we had a variable speed motor, the current would change the speed of the motor, and we'd have to also, and that's why we said we wanted to measure pressure, so that we could sort of connect the motor speed and the pressure, so we could actively control it.
I know you talked about turning it up to 2 times the heat rate. At the same time, you're going to control the diameter. So how are you going to deal with that?
It's sort of, you have a target drive speed to get that extrusion rate, and then that drive speed will vary slightly to control the pressure and control the die temperature. But ideally, it will be still around the same die extrusion rate. And another complicated controls question would be tying the extrusion speed with the spooling speed, because to maintain constant spooling tension, you have to have those be coupled. So that's another layer of complexity in the controls question about how to tie it all together and make sure that you don't slow down your production of filament, but your spooling goes the same speed and you end up necking again. That answer your question?
So there must be another variable.
Motor torque. We can change the motor torque as well. We can throw a new motor in.
There's also a range of temperatures that you can extrude ABS.
But the other variable that we can change that changes our extrusion rate would be the die orifice. If we crank up the motor speed, it's going to crank up the pressure, so we could change our die size so we compensate for the die swell.
Any other questions? Pete?
Yes, we
have not. We'd like to, and we think that because of the way 3D printers work, if you look at some of the samples of the used filament, the commercial filament, you'll see there's some knurls, because that actually came from a 3D printer, and the filament is crushed between 2 wheels before it's pushed through a nozzle. And we think even though we're below the filament diameter, we could successfully extrude with our filament. We just didn't have time. That was the question. We have not, but we'd like to.